Somewhere in the quiet vastness of space, beyond the gentle blue glow of Earth, there are worlds that have never felt wind, never heard oceans, never known the soft rhythm of rain falling onto soil, and yet for centuries humanity has looked toward those silent planets and imagined something impossible, something tender and bold at the same time. The idea that one day we might not simply visit them, but change them, reshape them, breathe life into them, and call them home. Terraforming is not merely a scientific proposal, it is a dream woven from curiosity and patience, a slow-burning question whispered beneath starlight. What if a dead world does not have to remain dead forever? When we gaze at Mars through telescopes, watching its red deserts glow faintly in the darkness, or when we imagine the frozen moons drifting around distant gas giants, we are not just observing rocks and ice. We are seeing blank canvases suspended in the cosmic ocean, waiting. The concept itself feels almost mythic, like something drawn from ancient legends where gods sculpted landscapes and summoned seas. But today it is scientists and engineers who quietly study atmospheres, magnetic fields, temperatures, and chemistry, wondering whether human hands could one day perform a transformation that would take centuries to unfold. Terraforming asks us to think not in years or decades, but in epochs, to imagine time stretching gently forward as machines warm a planet's crust, as greenhouse gases thicken a sky that was once thin and brittle, as frozen carbon dioxide melts and begins to form clouds, and as the first drops of artificial rain touch alien ground for the very first time. It is a story not of conquest, but of patience, because changing a world would never be sudden. It would be a slow awakening, like watching winter gradually soften into spring. In the silence of space, planets are shaped by gravity and chance, by volcanic fire and asteroid impacts, but terraforming introduces a new force into that ancient process: intention. Humanity, small and fragile on its pale blue sphere, has already changed one planet without fully meaning to, altering climates and landscapes through industry and expansion, and now the question gently emerges. If we have learned how to change a world accidentally, could we ever learn how to change one deliberately, carefully, responsibly? Imagine standing on the surface of Mars centuries from now, beneath a sky that is no longer pale and dusty but faintly blue, thin clouds drifting above distant mountains, and in the distance a shallow sea reflecting a quiet sun. Imagine knowing that this transformation began with ideas whispered in laboratories long ago, with equations written on white boards, with simulations run in quiet rooms where scientists dreamed in numbers. The beauty of terraforming lies in its scale. It is the art of thinking planetary thoughts, of seeing an entire world as a system that can be gently nudged, warmed, shielded, seeded. Yet it also carries a softness, because beneath all the engineering and astrophysics is something deeply human: the desire to belong, to expand the circle of habitable places, to ensure that life, fragile, breathing life, is not confined to a single shore in an infinite cosmic sea. As we float here on Earth, protected by our magnetic field and wrapped in our thick atmosphere, it is easy to forget how rare such balance may be, how delicate the dance of temperature and chemistry must be to allow oceans to remain liquid and air to remain breathable, and terraforming is ultimately an attempt to recreate that dance somewhere else, step by careful step. There is mystery here too, because no one truly knows whether we will succeed. The universe does not promise cooperation, and distant planets do not easily surrender their frozen or barren states. But the dream persists, carried forward by each new generation that looks upward at night and feels both small and limitless at the same time. Perhaps terraforming is less about transforming planets and more about transforming ourselves, teaching us to think long-term, to consider consequences that unfold over centuries, to act not just for immediate gain but for futures we may never personally see. The thought is both humbling and strangely comforting. Somewhere beyond our atmosphere, quiet worlds drift through darkness, unaware that tiny beings on a blue planet are imagining giving them skies and rivers, forests and wind. And as we begin this journey into the science and philosophy of terraforming, we move gently from fantasy into possibility, from distant speculation into real experiments already taking place. Because even now researchers are testing how plants might grow in simulated Martian soil, how microbes could survive extreme cold, how mirrors in orbit might reflect sunlight downward to warm frozen plains. The dream is no longer purely science fiction. It is a slow, unfolding conversation between imagination and reality. So let us drift deeper into this cosmic idea, slowly, calmly, like stardust carried on a silent current, and explore how humanity might one day turn a red desert into a blue horizon, how we might coax warmth from cold stone, and how, in the endless night of space, we may attempt the most ambitious act ever conceived, the gentle awakening of another world. Before we can ever imagine giving life to another world, we must first understand why so many worlds grow silent in the first place, why some planets cradle oceans beneath soft skies while others drift through space as frozen deserts or scorched wastelands, their surfaces etched by radiation and time. In the early days of a solar system, planets are born from swirling disks of dust and gas, chaotic and luminous, colliding and merging in a slow gravitational dance. And in those violent beginnings, the fate of each world is quietly decided by mass, distance, chemistry, and 1,000 subtle variables that shape its future. A planet's ability to hold onto an atmosphere is one of the most delicate balances in all of nature, because air itself is not fixed. It is a fragile veil of molecules constantly trying to escape into space, tugged upward by thermal energy and stripped away by solar wind. Earth retains its atmosphere because it is heavy enough, warm enough, and protected enough, wrapped in an invisible magnetic shield that deflects charged particles streaming from the sun, but not all planets are so fortunate. Imagine Mars billions of years ago, not the cold red desert we see today, but a world with rivers carving shallow valleys and perhaps even vast northern seas reflecting a pale young Sunday. Something changed. Over time, Mars lost much of its internal heat, its molten core slowed, and with that slowing the magnetic field weakened and eventually faded, leaving the atmosphere exposed to the relentless breath of solar wind. Without that magnetic armor, lighter molecules were gradually stripped away, escaping into the dark, and as the atmosphere thinned, the surface pressure dropped, liquid water could no longer remain stable, and the planet's warmth dissipated like a fading ember. Terraforming begins with this quiet tragedy, because to restore a world we must understand how it fell into stillness. Venus offers another story, equally dramatic but in the opposite direction, a cautionary tale of excess rather than loss. Similar in size to Earth, Venus may once have possessed oceans and temperate conditions, but positioned closer to the Sun it absorbed more energy, and as water vapor accumulated in its atmosphere it intensified the greenhouse effect, trapping heat in a feedback loop that spiraled beyond control. The oceans evaporated, hydrogen escaped into space, and what remained became a crushing blanket of carbon dioxide so dense and hot that lead would melt on its surface. One planet froze, another burned, and between them Earth held a narrow equilibrium, a reminder that habitability is not a default state but a rare alignment of forces sustained over immense stretches of time. Even giant planets like Jupiter tell a different chapter of planetary evolution, gathering enormous masses of gas during formation and becoming too massive to ever offer solid ground, yet influencing smaller worlds through gravity, redirecting comets, and shaping orbital patterns. Everywhere we look, planetary histories reveal how fragile atmospheres can be, how temperature, magnetic protection, volcanic outgassing, and solar radiation form an intricate system in which a slight imbalance can tip a world toward sterility. Volcanic activity itself plays a paradoxical role, because while eruptions can seem destructive, they also replenish atmospheres with gases like carbon dioxide and water vapor, sustaining greenhouse warmth and surface pressure. A geologically active planet breathes in its own way, cycling materials between core and crust, renewing its protective blanket of air, whereas a geologically quiet planet may slowly suffocate. When scientists study terraforming, they often begin by asking whether a planet can be encouraged to breathe again, whether buried carbon dioxide locked in ice caps or mineral deposits could be released to thicken the air, whether artificial magnetic shields placed in strategic orbital positions might mimic the protection of a natural dynamo. These ideas arise directly from studying why planets change over billions of years without intervention, because terraforming would mean accelerating or redirecting processes that normally unfold over geological timescales. There is something humbling in this perspective, realizing that a world's fate is not sealed by a single event but by an ongoing interplay of forces that either sustain or erode its delicate equilibrium. The story of planetary death is rarely sudden. It is gradual, a thinning, a cooling, a warming beyond control, a quiet erosion of balance that may take millions of years to fully manifest. And yet within that slowness lies hope. Because if change can occur naturally through physics and chemistry alone, then perhaps guided change is not entirely beyond imagination. We must learn from the scars etched into Martian valleys and the inferno hidden beneath Venusian clouds, not as distant curiosities but as lessons written in stone and atmosphere. Each crater, each layer of sediment, each measurement of isotopic ratios collected by orbiters and rovers tells us how climates evolve and collapse, how oceans disappear, how skies grow toxic or vanish into vacuum. To terraform responsibly would require patience equal to planetary time, a recognition that we are entering a system older and more powerful than ourselves. As we drift through these thoughts, it becomes clear that terraforming is not simply about adding air or heat. It is about restoring balance to a world that has slipped too far in one direction, either into freezing silence or runaway fire. The universe does not easily create habitable planets, and once a world loses its breath it rarely regains it unaided. But in understanding why planets die, we begin to see faint pathways toward revival, subtle levers that might be pulled gently over centuries. The silence of Mars is not absolute. Traces of its former warmth remain locked in ice and mineral veins, whispers of a time when it may have known flowing water. And so our journey continues, deeper into the mechanics of atmospheres and magnetic shields, into the slow heartbeat of planetary cores, as we ask not only how worlds perish, but how they might, with careful guidance, breathe once more. Of all the silent worlds circling our sun, Mars has always felt the most familiar, the most quietly inviting, as though it were waiting just beyond reach, glowing red in the night sky like an ember that refuses to fade. And for centuries humanity has looked toward it not as a distant stranger but as a possible second chapter in our planetary story. Even before spacecraft crossed the void to study it closely, ancient astronomers traced its movements across the heavens, noting its restless wandering among the stars, unaware that beneath its rust-colored glow lay a landscape carved by water long ago. When modern probes finally arrived, orbiting and landing upon its surface, they revealed something astonishingly gentle and haunting: dry river valleys etched into stone, deltas shaped like fans spreading into ancient basins, minerals that form only in the presence of liquid water, and polar caps of frozen carbon dioxide and water ice shimmering faintly under a pale sun. Mars was not always the cold desert we see today. Billions of years ago it may have known rain, perhaps even shallow seas stretching across its northern plains, reflecting a thicker atmosphere and a warmer sky. Something was lost there, a planetary breath that slowly thinned and drifted into space, leaving behind a fragile atmosphere less than 1% as dense as Earth's, too thin to hold warmth, too delicate to protect liquid water from instantly boiling away under the low pressure. Yet in its silence lies possibility, because Mars still holds the ingredients of transformation locked within its frozen soil and polar caps, waiting like seeds buried beneath winter frost. Scientists see in Mars not perfection, but potential. It is close enough to Earth to reach within months, similar enough in day length and axial tilt to allow seasons, and solid enough beneath its surface to build upon, and these subtle alignments make it the first true candidate in humanity's dream of terraforming. Imagine standing upon its surface at twilight, watching the sun set in hues of blue through thin dust-filled air, the horizon stretching endlessly in quiet stillness, and feeling the immense scale of what would be required to change such a world. Terraforming Mars would begin not with forests or oceans, but with warmth, because temperature is the first gatekeeper of habitability. The planet sits farther from the sun than Earth, receiving less solar energy, and its thin atmosphere allows precious heat to escape into space each night, causing dramatic temperature swings between day and night. To warm Mars, scientists have imagined amplifying the greenhouse effect deliberately, releasing carbon dioxide trapped in its polar ice caps and regolith, thickening the atmosphere until it can retain more heat, until ice begins to melt and pressure slowly rises. Some have proposed orbiting mirrors that reflect sunlight downward, gently raising temperatures over decades. Others envision factories producing powerful greenhouse gases far stronger than carbon dioxide, designed specifically to trap warmth efficiently. These ideas unfold slowly, not as explosive interventions but as patient adjustments, nudging Mars toward a tipping point where warming feeds upon itself, releasing more gas, creating thicker clouds, building momentum over centuries. Yet warming alone would not be enough, because without protection from solar wind the atmosphere could once again erode, just as it did in the distant past when Mars lost its magnetic shield. Here the dream grows even more ambitious, imagining vast magnetic generators placed at strategic positions in space, perhaps near the Martian L1 point between Mars and the Sun, creating an artificial magnetic field that deflects charged particles and shields the rebuilding atmosphere. It sounds almost like science fiction, yet the principles are grounded in physics we already understand, scaled to planetary dimensions. As pressure increases and temperatures rise, water ice locked in soil could melt seasonally, forming shallow streams that flow briefly before freezing again, gradually carving new channels into ancient terrain. Over generations, microbial life, hardy extremophiles engineered or adapted for Martian conditions, might be introduced, organisms capable of surviving cold and low pressure, slowly modifying soil chemistry, producing oxygen as a byproduct of photosynthesis under a dimmer sun. The transformation would not be immediate, it would span lifetimes beyond our own, a multi-generational endeavor requiring patience deeper than ambition. Yet Mars offers something uniquely compelling, evidence that it once held many of the features we seek to restore. Its valleys whisper of rain, its mineral deposits remember water, its layered sediments preserve a climate archive written in stone. Terraforming Mars would not mean inventing a world from nothing, but reawakening a world that once hovered near habitability before slipping into cold dormancy. There is comfort in that thought, as though Mars is not entirely alien but simply asleep. Even now robotic explorers traverse its plains, analyzing soil, drilling into rock, mapping ice beneath the surface, each mission adding clarity to the long question of feasibility. The journey toward terraforming begins with knowledge, with understanding every nuance of Martian geology, every seasonal shift in atmospheric pressure, every dust storm that envelopes the planet in global haze. And as we imagine the red planet slowly shifting in color over centuries, from rust to muted brown, from brown to hints of green as engineered mosses cling to sheltered valleys, we are not merely fantasizing about expansion, but exploring what it would mean to steward another world responsibly. Mars stands as both challenge and invitation, a silent neighbor offering just enough familiarity to spark hope, yet enough harshness to demand humility. In its frozen deserts we see both the fragility of habitability and the resilience of planetary systems waiting to be nudged back toward equilibrium. And so, as our exploration deepens, we carry forward the image of Mars not as a barren wasteland, but as the first candidate in humanity's most ambitious experiment, the careful, deliberate awakening of a sleeping world beneath a distant, patient sun. To warm a planet is to challenge the quiet mathematics of sunlight and shadow, to gently alter the invisible exchange between radiation and atmosphere that determines whether a world shivers in frost or basks in temperate calm. And when we imagine warming Mars, we are imagining the slow adjustment of a planetary thermostat that has been set too low for billions of years. Every planet lives within an energy balance, receiving light from its star and radiating heat back into space, and the thickness and composition of its atmosphere decide how much of that heat lingers near the surface like a protective blanket. On Earth, greenhouse gases such as carbon dioxide and water vapor trap warmth in a delicate equilibrium that allows oceans to remain liquid and life to flourish. But on Mars the blanket is threadbare, thin and fragile, allowing precious heat to escape each night into the cosmic dark. To terraform Mars, the first gentle act would be to thicken this atmospheric veil, not with reckless speed but with steady intention, increasing surface pressure until liquid water can persist without instantly boiling away. Scientists have studied the polar caps of Mars closely, discovering that they contain vast reserves of frozen carbon dioxide layered over water ice, and these icy stores represent potential building blocks for atmospheric renewal. If temperatures could be raised even slightly, perhaps through reflective mirrors placed in orbit to redirect additional sunlight toward the poles, the carbon dioxide ice would begin to sublimate, turning directly from solid to gas, thickening the atmosphere in a gradual cascade. As pressure rises, the greenhouse effect would intensify, trapping more heat and causing additional ice to release gas, creating a feedback loop that could slowly amplify warming over decades or centuries. This process would not resemble a sudden ignition, but rather the slow dawn of spring after an endless winter, each incremental change building upon the last. Some researchers have imagined constructing vast orbital mirrors, shimmering structures positioned carefully so that sunlight is concentrated onto selected regions, perhaps beginning at the poles where frozen reserves lie waiting. These mirrors would not scorch the surface but gently enhance solar input, a controlled increase designed to tip the planet toward a warmer state. Others have proposed releasing synthetic greenhouse gases far more potent than carbon dioxide, molecules engineered to trap infrared radiation efficiently and persist in the thin Martian air, accelerating the warming process while natural feedback mechanisms take hold. Such interventions would require extraordinary care, because altering a planet's climate is not a simple equation. It is a symphony of variables interacting in subtle ways. Dust storms on Mars already play a role in its climate, occasionally enveloping the planet in a haze that absorbs sunlight during the day and traps heat at night, and understanding these cycles would be essential before attempting any deliberate modification. As the atmosphere thickens and temperatures rise, frozen water beneath the surface could begin to melt seasonally, forming transient streams that carve new channels across ancient terrain. These first trickles of liquid water would mark a profound shift, signaling that Mars has crossed a threshold from static cold into dynamic change. Yet warming alone does not guarantee stability. Without a protective magnetic field, the newly thickened atmosphere would remain vulnerable to erosion by solar wind, slowly stripped molecule by molecule over time. Some visionary concepts suggest placing a powerful magnetic shield at a strategic point between Mars and the Sun, perhaps near the L1 Lagrange point, generating a field strong enough to deflect charged particles and preserve the rebuilding atmosphere. Though such a structure would be immense, the physics behind it are well understood, extending principles already used in smaller-scale technologies. In this way, terraforming becomes not a single action but a coordinated orchestration of heat, chemistry, and protection, each element reinforcing the others in a gradual transformation. As decades pass and pressure increases, the sky itself might begin to change in color and character, thickening from a faint salmon haze into something deeper, perhaps tinged with pale blue during midday as sunlight scatters through denser air. Clouds could form more frequently, first thin and icy, then thicker as water vapor accumulates, drifting across the horizon in slow-moving bands. The surface temperature, once swinging wildly between day and night, would moderate slightly, softened by the insulating presence of air. These changes would not occur within a single human lifetime, and those who initiated the process might never witness its culmination, but terraforming has always required thinking beyond individual horizons, embracing the idea that some endeavors are meant to unfold across generations. There is a quiet poetry in imagining engineers and scientists planting the first seeds of planetary warming, knowing that centuries later descendants may walk beneath a transformed sky and trace its origins back to those early experiments. The act of warming a frozen planet is not about domination. It is about partnership with physics, working alongside natural processes rather than against them, amplifying tendencies already present within the planet's own materials. Carbon dioxide locked in ice is not foreign to Mars. It is part of its history, part of its original atmosphere that once allowed rivers to flow. By releasing it deliberately, we would be coaxing the planet back toward a state it may once have known, carefully guiding it toward equilibrium. And as we contemplate the slow ignition of a new climate on Mars, we are reminded that warmth itself is a fragile gift in the cosmos, rare and easily lost, yet powerful enough to awaken entire worlds from dormancy. The dream of terraforming continues to unfold in this patient rhythm, step by step, degree by degree, until the red planet begins to feel the faint, steady pulse of renewed heat beneath a sky slowly learning how to hold it. If warming a frozen planet is like striking the first quiet match in a long night, then building a sky is the slow tending of that flame, protecting it, feeding it, allowing it to grow until it becomes something steady and enduring, because a world without atmosphere is not merely cold, it is exposed, vulnerable to radiation, to meteor impacts, to the silent erosion of solar wind. And so the dream of terraforming must eventually turn toward the patient construction of air itself. On Mars today, the atmosphere is thin beyond comfort, a fragile envelope composed mostly of carbon dioxide, pressing down with less than 1% of the pressure we feel on Earth, so slight that liquid water cannot persist, so delicate that a human standing there would require layers of protection just to survive a breath. To thicken this atmosphere is not simply to add gas, but to change the very experience of standing on the surface, to allow wind to carry dust in softer currents, to let sound travel with greater depth, to create a pressure strong enough for water to remain liquid under open sky. The process would begin with the gases already present, locked within polar caps and mineral deposits, gently released through warming, but over time this would not be enough. Additional sources would need to be found or created, perhaps through chemical factories operating autonomously across the plains, extracting elements from regolith, releasing engineered greenhouse compounds, slowly layering molecule upon molecule into the growing sky. There is something almost artistic in imagining this gradual layering, as if painting transparency into opacity, turning invisibility into substance. As the atmosphere thickens, even slightly, it would begin to change the way sunlight interacts with the planet, scattering differently, softening shadows, deepening colors at sunrise and sunset. Yet a thick carbon dioxide atmosphere alone would not be breathable, and so the longer journey would turn toward oxygen, that delicate and reactive gas that on Earth is produced largely by living organisms through photosynthesis. The introduction of life into a transforming world would be one of the most profound steps in terraforming, not complex forests at first, but microscopic pioneers, extremophiles capable of surviving harsh ultraviolet radiation, low temperatures, and thin air. Certain microbes on Earth already thrive in extreme deserts, in polar ice, in high-altitude environments where oxygen is scarce and sunlight is intense, and scientists study these resilient forms carefully, imagining how they might adapt to Martian conditions or be gently engineered to endure them. These microorganisms could slowly begin altering the chemical balance of the atmosphere, consuming carbon dioxide, releasing trace amounts of oxygen over generations, their colonies spreading gradually across sheltered valleys where liquid water appears seasonally. This transformation would be measured not in years but in centuries, because oxygen accumulation is slow, requiring immense biomass to change atmospheric composition meaningfully. During this time, the sky of Mars would likely remain dominated by carbon dioxide, but subtle shifts would occur, detectable first by instruments, then by future inhabitants watching the air evolve over lifetimes. There is a quiet parallel here with Earth's own history, because our planet was not always oxygen-rich. Billions of years ago, before the Great Oxygenation Event, Earth's atmosphere was largely devoid of free oxygen, until cyanobacteria in ancient oceans began producing it as a waste product, slowly transforming the chemistry of the entire planet and paving the way for complex life. Terraforming Mars would echo this ancient transformation, compressing geological timescales into deliberate, guided change. Yet building a sky is not solely about chemistry, it is about retention and protection. Without a magnetic field, the growing atmosphere would remain vulnerable to solar stripping, and so the idea of an artificial magnetic shield returns, acting as a guardian for the evolving climate. If such protection could be established, the thickening atmosphere might endure for millennia, allowing water cycles to stabilize, clouds to persist, perhaps even precipitation patterns to emerge. Over time, as oxygen levels rise incrementally, future settlers might transition from fully sealed habitats to semi-open environments, wearing lighter protective gear, eventually breathing through filters rather than tanks, until one distant day breathable pockets of air might exist in low-lying basins where pressure is greatest. Even then, the atmosphere might never match Earth's density exactly. Mars has lower gravity, and some gases would inevitably escape over time, requiring maintenance and renewal, making terraforming not a finished project but an ongoing stewardship. This idea shifts the narrative from conquest to caretaking. recognizing that a built sky must be nurtured continuously. As pressure increases, dust storms that once raged across the planet with violent speed might behave differently, shaped by thicker air into more structured weather systems. Clouds of water ice and perhaps carbon dioxide would form and dissipate in rhythms that begin to resemble climate rather than mere atmospheric fluctuation. The sky itself would become dynamic, no longer a static pink haze but a living system responding to temperature gradients and planetary rotation. In imagining this transformation, one begins to sense how profoundly atmosphere defines experience. It determines how light falls, how heat lingers, how life interacts with environment. To build a sky is to grant a planet softness, to buffer it against extremes, to allow it to cradle liquid water and shield delicate organisms from radiation. And as we drift through this vision of molecule-by-molecule construction, we see terraforming not as an act of sudden creation but as the slow weaving of a protective cloak around a once barren world. A cloak that may take centuries to complete, yet once established could whisper with wind and cloud, turning silent horizons into breathing landscapes beneath a sky patiently, carefully made. There is a moment in every world's history when water decides whether it will remain locked in silence or begin to move, and movement is everything, because water in motion carves valleys, carries minerals, shapes coastlines, and whispers the first lullabies of habitability across stone. On Mars today, water exists mostly as memory and ice, frozen within polar caps and hidden beneath regolith, preserved like a relic of a warmer era. But if warmth and atmospheric pressure were to rise steadily over centuries, something extraordinary would begin to happen beneath that rust-colored surface. Ice would soften, frost would retreat. Molecules that have slept for billions of years would stir, slipping from solid to liquid, pooling briefly before evaporating, testing the new conditions of a thickening sky. At first, these appearances of liquid water would be fragile and fleeting, forming in equatorial regions during the warmest seasons, only to vanish as temperatures dipped again at night. But as the greenhouse effect strengthened and the atmosphere grew denser, those transient flows could lengthen, lingering longer each year, carving subtle channels that echo ancient riverbeds already etched into Martian terrain. It is astonishing to realize that Mars already bears the scars of flowing water, vast networks of valleys that mirror river systems on Earth, deltas that once emptied into basins, and layered sediments that hint at long-vanished lakes. Terraforming would not be inventing rivers from nothing. It would be reawakening the pathways carved long ago, allowing water to retrace old routes as though remembering its former home. Over time, as polar carbon dioxide sublimated and pressure increased, deeper reservoirs of water ice could begin melting more consistently, feeding into low-lying basins where gravity gently gathers fluids. These basins, particularly in the northern hemisphere, have long been theorized as the remnants of ancient oceans, and in a warmed future they might once again fill slowly, reflecting pale sunlight in shimmering expanses that stretch toward distant horizons. The formation of even shallow seas would mark a turning point, because large bodies of water moderate climate, absorbing heat during the day and releasing it slowly at night, smoothing temperature extremes and fostering more stable weather patterns. Clouds would thicken as evaporation increases, drifting across the sky in evolving shapes, sometimes condensing into precipitation that falls not as snow alone, but as the first tentative rain. Imagine standing beneath that moment, the first rainfall on Mars in billions of years, droplets descending through air that finally holds enough pressure to cradle them, striking dusty soil with a sound never before heard by human ears on that world. The impact would be subtle, gentle, yet immeasurably profound. Rain would seep into porous ground, perhaps nourishing microbial colonies introduced earlier in sheltered regions, spreading moisture across landscapes once defined by aridity. Over centuries, a hydrological cycle could begin to stabilize, evaporation feeding clouds, clouds feeding precipitation, precipitation carving new channels and replenishing shallow seas. Of course, Mars' lower gravity and colder average temperatures would shape this cycle differently from Earth's. Oceans might remain shallower, polar regions more prone to seasonal freezing, and evaporation rates distinct. But the fundamental rhythm, water rising, condensing, falling, flowing, could establish itself once more. The reappearance of liquid water would also alter chemistry dramatically, dissolving minerals, transporting salts, and reshaping soil composition, gradually creating more hospitable substrates for plant life in the distant future. Water is often called the universal solvent, and in terraforming it would act as both sculptor and sustainer, reshaping terrain while enabling biological processes to expand. Yet caution would be essential because too rapid a release of greenhouse gases or excessive warming could destabilize the delicate balance sought, potentially triggering runaway effects reminiscent of Venus, though Mars' distance from the Sun makes such extremes less likely. The process would demand careful monitoring across generations, adjusting atmospheric composition and solar input with patience and restraint. As seas form, they would reflect the sky, creating a visual transformation as dramatic as any chemical shift. Where once there was endless red dust, there would now be horizons shimmering with blue or perhaps greenish hues depending on mineral content. Coastlines would emerge gradually, irregular and ancient, shaped by both old topography and new erosion. Future settlers might build habitats along these shores, watching tides that are subtle but present, influenced by Mars' two small moons, Phobos and Deimos, casting faint shadows over growing waters. The presence of open water would also offer psychological comfort to human inhabitants, echoing Earth's familiar landscapes, creating a sense of belonging in an otherwise alien world. Water softens a planet not only physically but emotionally. It introduces sound, movement, reflection, and the promise of life. In imagining rivers winding once again across Martian plains, one senses that terraforming is as much about restoring motion as it is about raising temperature or pressure. A world with flowing water feels alive, dynamic, capable of change. And as centuries pass in this vision, oceans deepen slowly, rains grow more frequent, and the red planet begins to shimmer under clouds that drift with quiet purpose. The transformation would not erase Mars' identity. Its gravity would remain lighter, its skies perhaps slightly different in hue, its landscapes uniquely shaped by its history. But beneath that evolving sky, water would once again carve valleys and gather in basins, whispering across stone that the long dormancy has ended. The return of water would mark the transition from engineering experiment to living system, from controlled intervention to self-sustaining cycles. And in that shift lies the heart of terraforming, not domination, but the gentle reintroduction of nature's most essential rhythm, flowing patiently across a once frozen world now learning how to breathe and reign and remember what it once was. Long before forests could sway beneath an alien sky, before grasses could ripple across plains or trees could anchor themselves in softened soil, life would have to arrive quietly, almost invisibly, in forms so small they might escape notice entirely, and yet these first pioneers would carry within them the power to alter an entire planet. The greening of a world does not begin with towering plants or blooming landscapes. It begins with microbes, with resilient organisms that can endure extremes, that can survive where conditions remain fragile and incomplete. On a slowly warming Mars, where water has begun to flow seasonally and the atmosphere has thickened enough to soften radiation slightly, the first biological step would likely involve extremophiles, microorganisms adapted to harsh environments on Earth, capable of tolerating cold deserts, high ultraviolet exposure, and low nutrient availability. Scientists already study microbes that live in Antarctica's dry valleys, in high-altitude plateaus, and even within rocks in arid regions, organisms that persist with minimal water and limited protection, and these forms of life offer a glimpse of how biology might take root on a terraforming planet. The introduction of such microbes would not be a reckless scattering, but a careful selection process guided by decades of research, ensuring that each species introduced could contribute to soil formation, atmospheric change, or nutrient cycling without destabilizing the fragile equilibrium being built. When microbes settle into regolith, the loose, dusty soil covering Mars, they begin subtle transformations, breaking down minerals, releasing trace nutrients, altering pH levels, and slowly converting sterile ground into something more hospitable. These processes are nearly invisible at first, unfolding over years and decades, yet collectively they reshape chemistry in ways that make future life possible. Some engineered cyanobacteria might perform photosynthesis even under dimmer sunlight, consuming carbon dioxide and releasing oxygen in small but steady amounts, gradually enriching the air over centuries. This oxygen would not accumulate quickly, and it would likely remain at trace levels for generations, but each molecule released would represent a step toward a more breathable future. Alongside microbes, the next wave might include hardy lichens and mosses, organisms that represent partnerships between fungi and photosynthetic partners, capable of surviving on bare rock, tolerating extreme temperature swings, and slowly spreading across damp surfaces. Moss, in particular, evokes a quiet resilience. It does not demand fertile soil or abundant nutrients, but thrives in minimal conditions, forming soft green carpets that trap moisture and protect underlying substrates. Imagine patches of moss clinging to sheltered Martian valleys where seasonal meltwater flows, their delicate filaments capturing sunlight beneath a sky still tinted faintly red, their presence marking the first visible shift in planetary color. Over decades, these pioneer species would contribute organic material as they grow and die, enriching soil with carbon compounds, gradually building a layer of biological complexity that can support more demanding plants in the distant future. The process mirrors Earth's own ecological succession, where barren landscapes after volcanic eruptions or glacial retreats are first colonized by microbes and lichens before giving way to grasses and eventually forests. Terraforming would accelerate and guide such succession, compressing timelines while respecting the underlying principles of ecology. Yet introducing life to another world raises profound ethical and philosophical questions, because Mars, even if currently lifeless, possesses its own geological history and perhaps even traces of ancient microbial existence yet undiscovered. The decision to seed it deliberately would require certainty that no indigenous life remains, a responsibility not taken lightly. If Mars were confirmed sterile, then the introduction of life could be seen not as invasion but as restoration, granting a once habitable world a second chance at biological richness. As green patches expand slowly across the landscape, subtle changes would ripple outward. Photosynthetic organisms would darken the surface in places, slightly reducing albedo and absorbing more sunlight, contributing incrementally to local warming. Soil structure would improve as microbial mats bind particles together, reducing dust storms and stabilizing ground in select regions. Over centuries, oxygen concentrations might rise enough to support more complex plant species introduced gradually, perhaps hardy grasses or genetically adapted shrubs capable of surviving lower gravity and cooler climates. Each stage would depend on the success of the previous one, a delicate ladder of biological complexity built rung by rung. There is a certain poetry in imagining the first green on Mars, not as a sudden transformation into lush forests, but as scattered, humble growth in sheltered niches, expanding outward slowly year by year. These early ecosystems would likely be fragile and carefully monitored, with human caretakers adjusting variables, providing additional nutrients, perhaps even constructing protective domes to test plant communities before allowing them to spread more widely. Life would not overwhelm the planet. It would negotiate with it, adapting to lower gravity, different day lengths, cooler temperatures, evolving alongside engineered atmospheric changes. The presence of green would also reshape human perception of the planet, shifting it from barren frontier to living landscape, deepening emotional connections for those who dwell there. Over generations, children born beneath a thickening Martian sky might grow accustomed to seeing moss-covered slopes and shallow wetlands shimmering in low gravity, unaware of how extraordinary their world once seemed to those who first imagined its transformation. Seeding life is perhaps the most intimate act of terraforming, because it involves not machines or mirrors, but living systems capable of growth, reproduction, and adaptation. It acknowledges that a habitable world is not merely warm and wet, but biologically active, alive with processes that sustain themselves. And as microbes multiply quietly, as moss spreads in gentle patterns across red soil, Mars would begin to shift from engineered project to evolving ecosystem, its surface no longer defined solely by stone and dust, but by the subtle, persistent emergence of green, the first visible sign that a once silent world has begun to breathe not only air and water, but life itself. When we speak of terraforming, it is tempting to imagine grand machines igniting rapid change, mirrors flashing in orbit, factories humming across alien planes, atmospheres thickening in dramatic surges, but the deeper truth is far quieter and far more patient, because the true architect of planetary transformation is not technology alone, but time itself. Time is the silent engineer that shapes mountains, fills oceans, erodes valleys, and alters climates, and any attempt to remake a world must ultimately surrender to its slow authority. Even with advanced engineering, warming a planet, thickening its atmosphere, restoring water cycles, and seeding life would unfold across centuries, perhaps millennia, stretching far beyond the lifespan of those who begin the process. This reality changes the nature of the endeavor completely, turning terraforming from a project into a legacy, from a mission into a generational story that passes quietly from parent to child, from teacher to student, from one era to the next. Imagine the first settlers who stand beneath a thin Martian sky and initiate the early stages of atmospheric warming. They would know with certainty that they will never walk beside open oceans there, never breathe unfiltered air, never see forests rise from regolith, and yet they would begin anyway, planting seeds of change whose fruition lies far beyond their own years. There is something profoundly humbling in committing to an outcome you will never personally witness, in shaping conditions for lives not yet born, and in this way terraforming becomes not only a scientific challenge but a philosophical one, demanding patience that mirrors planetary timescales. On Earth, we often measure progress in quarters, in election cycles, in decades at most, but a terraformed world demands thinking in centuries, in epochs that require continuity of purpose across shifting cultures and technologies. Time smooths abrupt edges, allowing gradual adjustments to stabilize rather than destabilize, and many of the processes involved in terraforming would rely on feedback loops that require careful observation over long durations. The release of greenhouse gases to warm Mars, for example, would need to be monitored year after year, ensuring temperatures rise steadily but not excessively, adjusting interventions gently to avoid tipping into imbalance. The growth of microbial ecosystems would demand decades of ecological study, observing how introduced organisms adapt, evolve, and interact with newly formed soils and water bodies. In this sense, terraforming would resemble gardening on a planetary scale, where the gardener cannot rush growth but must nurture conditions and wait patiently for seasons to unfold. Even the development of artificial magnetic shields or atmospheric factories would likely require maintenance and iteration across generations as technologies improve and unforeseen challenges arise. And yet, time also brings resilience. A system that evolves gradually has opportunities to stabilize, to correct minor instabilities before they escalate, to adapt organically alongside engineered inputs. Over centuries, Mars' climate might settle into rhythms of seasonal change, perhaps colder winters and mild summers by Earth standards, but stable enough to sustain expanding ecosystems. The first shallow seas would deepen slowly, coastlines shifting incrementally rather than violently, allowing biological communities to adapt in step with environmental change. Time would soften the dramatic into the natural, until future inhabitants perceive oceans and green valleys not as miracles, but as the quiet normalcy of their world. There is also a psychological transformation that accompanies long-term projects. The initial pioneers might feel awe and isolation, acutely aware of the planet's harshness and the fragility of early interventions, but their descendants could inherit a world already partially transformed, their sense of belonging rooted not in Earth's distant memory but in Mars' evolving landscape. Generations born under a thickening sky might grow up measuring change not in grand leaps but in subtle shifts, slightly denser air than their grandparents knew, slightly longer seasons of flowing water, slightly broader patches of green along once barren slopes. This incrementalism would shape culture itself, fostering patience, continuity, and stewardship as central values. Terraforming thus becomes as much a social evolution as a planetary one, requiring institutions capable of maintaining focus across centuries, education systems that teach planetary science not as abstract knowledge but as lived responsibility, and governance structures that resist the temptation of short-term gains in favor of long-term equilibrium. Time, in this vision, is not an obstacle but a collaborator, granting space for adjustment and learning. Mistakes made in early decades could be corrected gradually, feedback analyzed, strategies refined, ensuring that transformation remains measured rather than chaotic. Even the oxygenation of the atmosphere would unfold over centuries, echoing Earth's own slow transition billions of years ago when microbial photosynthesis gradually reshaped atmospheric chemistry. That ancient precedent reminds us that planetary change is rarely swift, and perhaps should not be. As we drift through this thought, we realize that terraforming is less about imposing speed upon nature and more about aligning human intention with natural tempo. The red planet would not awaken overnight. It would stir gently, responding to centuries of subtle nudges. Time would weave together engineering, ecology, and climate into a tapestry that no single generation could fully grasp in its entirety. And therein lies both challenge and beauty, the recognition that to terraform a world is to participate in a story longer than any one life, to plant forests whose shade you will never sit beneath, to warm oceans whose tides you will never feel. In embracing time as the greatest engineer, humanity would learn to measure success not in immediacy but in continuity, not in spectacle but in persistence. And as centuries pass beneath a sky slowly growing thicker and bluer, the transformation would feel less like a sudden conquest and more like a gradual remembering, as though the planet itself is rediscovering how to sustain warmth, water, and life, guided patiently by those who understood that the most powerful force in shaping a world is not speed, but time. As the vision of warming skies and returning oceans grows clearer in the imagination, another question rises just as steadily, quieter but no less profound, lingering in the space between ambition and responsibility. Should we change another world at all? Terraforming is not merely a technical endeavor. It is an ethical threshold, a decision that reaches beyond engineering into philosophy, into the meaning of stewardship, into our understanding of life's place in the cosmos. Mars, though barren to our current knowledge, is not empty of history. Its surface holds billions of years of geological memory, etched into canyon walls and layered sediments, a record of ancient rivers and vanished atmospheres. To alter that world would be to write a new chapter atop an old manuscript. And before doing so, humanity must ask whether any traces of indigenous life might still persist, perhaps hidden beneath the surface, preserved in subsurface ice or protected within mineral veins. The possibility, however remote, that Mars once hosted microbial life, or might still, transforms terraforming from a neutral act into a potentially irreversible one. If even a single native organism survived in some protected niche, introducing Earth life could overwhelm it, erasing a unique evolutionary lineage that arose independently of our own. The value of such life, even if microscopic, would be immeasurable, offering insight into biology's universality, into whether life arises easily in the universe or is a rare miracle. Therefore, planetary protection becomes the first ethical boundary, demanding exhaustive exploration and study before deliberate biological introduction. Only if Mars is confirmed lifeless would the moral calculus shift toward restoration rather than interference. Even then, another layer of reflection emerges. Does humanity possess the right to reshape entire planets simply because we can? On Earth, our history of environmental alteration carries both triumph and regret. We have cultivated landscapes and built civilizations, yet we have also disrupted ecosystems and destabilized climates. Terraforming invites us to carry that power outward into space, magnified to planetary scale. Some argue that extending life beyond Earth is not only permissible but essential, a safeguard against planetary catastrophe, a way to ensure that consciousness and biology endure even if Earth faces existential threats. In this view, spreading life is an act of cosmic resilience, transforming barren worlds into living systems that increase the universe's complexity and beauty. Others caution that the universe does not belong to us to modify, that barren planets possess intrinsic value as they are, untouched and pristine, representing natural states worthy of preservation. Between these perspectives lies a delicate balance, one that demands humility. Terraforming would not be a sudden imposition but a gradual, monitored process spanning centuries, allowing time for reconsideration and correction. It would require international consensus, transparent governance, and a framework that treats planetary environments as shared heritage rather than private property. The ethics of terraforming also extend to future generations, both on Earth and on the transformed planet. Those who initiate the process are making decisions that will shape environments centuries hence, determining atmospheric composition, climate patterns, and ecological trajectories for descendants who cannot consent to those choices. This temporal dimension adds weight to every intervention. We are not merely altering stone and air, but crafting living conditions for unborn societies. Such responsibility demands foresight and restraint, ensuring that no irreversible step is taken without exhaustive study and global agreement. There is also the psychological dimension to consider. Transforming a planet could alter humanity's relationship with nature itself. Would mastering planetary engineering foster deeper respect for ecosystems, recognizing the complexity required to sustain them, or might it encourage further hubris, reinforcing the illusion that environments are infinitely malleable? The answer depends on intention and culture. If terraforming is approached as stewardship, as a careful nurturing of balance informed by lessons learned from Earth's environmental challenges, it could cultivate a deeper planetary ethic, one that values equilibrium and sustainability above exploitation. But if driven by impatience or unchecked ambition, it risks repeating mistakes on a grander scale. Even the act of introducing life carries philosophical weight. Life on Earth evolved through billions of years of trial and adaptation. Transplanting it to another world is both a continuation of that evolutionary journey and a deliberate redirection of it. In seeding Mars with microbes and moss, we would be extending Earth's biosphere outward, transforming it from a single-planet phenomenon into a multi-world presence. This expansion could be seen as life's natural progression, echoing the way organisms spread across continents and oceans on Earth, yet the scale elevates it into unprecedented territory. Ultimately, the ethics of terraforming rest on intention, caution, and collective wisdom. It requires recognizing that a planet is not an empty canvas but a dynamic system shaped by time, deserving of study and respect before alteration. It asks whether our desire to create new homes is matched by our commitment to protect and sustain them responsibly. As we imagine green valleys emerging on Mars and rain falling upon once dusty plains, we must also imagine the deliberations, debates, and agreements that preceded those changes, the global conversations that determined whether and how such transformation should proceed. The moral dimension does not diminish the dream, rather, it deepens it, grounding aspiration in reflection. Terraforming, if ever undertaken, would represent one of humanity's most profound collective decisions, a choice to extend life beyond its birthplace while honoring the silent histories of other worlds. And in confronting that choice thoughtfully, we may discover that the greatest transformation required is not of Mars itself, but of our own understanding of responsibility in a universe vast enough to hold both wonder and consequence. If the story of terraforming begins with Mars, then its future inevitably expands outward, because humanity's dream of shaping worlds does not end with a single red planet. Beyond Mars lies an even more dramatic and dangerous candidate, Venus, a world that represents the ultimate warning of planetary climate imbalance. Venus is often called Earth's twin because of its similar size and gravity, yet its surface is hidden beneath crushing atmospheric pressure and temperatures hot enough to melt lead. The challenge of terraforming Venus would not begin on the surface, because no human could survive there. Instead, it would begin high above its clouds, where temperatures are cooler and pressures are closer to Earth-like conditions. Some scientists have imagined floating cities suspended in Venus's upper atmosphere, where human civilization could exist while gradually attempting to alter the planet below. The first step would involve reducing the immense carbon dioxide concentration that traps heat in a runaway greenhouse effect. Concepts have been proposed involving giant solar shades positioned between Venus and the Sun, reducing incoming solar radiation and allowing the planet to slowly cool. Over centuries, as temperatures drop, atmospheric chemistry could change, potentially allowing carbon dioxide to condense or be chemically processed into stable mineral forms. The vision is almost poetic, transforming a world of fire and clouds into one of oceans and continents. Yet the technical and ethical challenges are far greater than those of Mars. Venus teaches a powerful lesson. Terraforming is not only about adding life but also about removing excess energy and restoring equilibrium. Beyond the inner solar system, attention turns to the icy moons orbiting gas giants like Jupiter, particularly worlds such as Europa, which may hide vast oceans beneath kilometers of ice. These moons present a different type of terraforming challenge, because instead of warming frozen deserts, humanity might need to preserve existing subsurface oceans while creating breathable atmospheres above ice-covered surfaces. Europa's ocean is believed to contain more liquid water than all of Earth's oceans combined, but its surface is exposed to intense radiation from Jupiter's magnetic environment. Any attempt to colonize or terraform such a world would require protective habitats or radiation-shielding technologies. Some speculative ideas suggest heating localized regions of ice to create artificial skylight windows into subsurface oceans, allowing sunlight to penetrate and support photosynthetic life beneath protective domes. Other concepts focus on building settlements directly within ice layers, constructing tunnels and underwater habitats similar to Earth's polar research stations but on a planetary scale. These moons represent a different philosophy of terraforming, not transforming entire climates, but creating habitable niches within existing environments. Looking even farther outward, humanity begins to consider planets orbiting distant stars, known as exoplanets, where terraforming would require technologies far beyond our current capabilities. These worlds may orbit stars different from our own sun, with varying light spectra, gravity strengths, and atmospheric compositions. Terraforming such planets would require not just environmental engineering but interstellar travel itself, a challenge that forces humanity to think in terms of centuries or even millennia of exploration. In this future vision, terraforming becomes part of a broader cosmic migration of life. Rather than being confined to a single star system, biology could spread like seeds carried on stellar winds of technology and exploration. Yet distance introduces new ethical and practical questions. Should humanity terraform distant worlds before fully understanding them? Or should we preserve them as scientific archives of cosmic diversity? These questions echo earlier debates about Mars but expand them across galactic scales. Ultimately, terraforming beyond Earth reflects humanity's transformation as much as planetary transformation. It requires patience, cooperation, and technological mastery far beyond what any single civilization can achieve alone. The dream of reshaping worlds becomes the dream of becoming a species capable of thinking across star systems, across centuries, and across generations yet unborn. As we imagine cities floating in Venusian clouds, oceans hidden beneath icy moons, and distant exoplanets waiting beneath alien skies, we begin to understand that terraforming is not simply about finding new homes. It is about ensuring that life itself continues its cosmic journey, expanding slowly and thoughtfully into the silent darkness of space. And in that journey, every new world becomes not a conquest, but a continuation of life's long story across the universe. The future of terraforming will not belong solely to human hands. Instead, it will belong to machines, intelligent systems, and self-evolving technologies that can work across centuries without fatigue, without impatience, and without forgetting long-term goals. If humanity ever succeeds in transforming alien worlds, it will likely be through a partnership between biological intelligence and artificial intelligence, where advanced algorithms monitor planetary conditions continuously, adjusting climate variables with precision far beyond human capability. These future terraforming systems would operate like living organisms themselves, sensing temperature, pressure, radiation, and chemical composition, responding in real time to maintain balance. Artificial intelligence would become the planetary caretaker, making millions of micro-decisions every second to stabilize climates as they slowly evolve. Imagine networks of autonomous drones flying across Martian skies, measuring atmospheric density, dispersing greenhouse compounds in carefully controlled amounts, or planting microbial life in optimal locations. These machines would be designed for longevity, built with self-repairing materials capable of healing microfractures and replacing worn components using local resources. Nanotechnology would likely play a major role, with microscopic machines distributed throughout soil, water, and air, acting as planetary maintenance workers. These nanobots could regulate chemical balances, break down harmful compounds, and help convert carbon dioxide into useful organic molecules, accelerating ecological succession without overwhelming natural processes. Advanced robotics would also be essential for constructing massive infrastructure required for terraforming. Building orbital mirrors, magnetic shield generators, and atmospheric processing plants would require autonomous construction fleets capable of mining local materials and assembling large structures without constant human supervision. These machines would need sophisticated decision-making capabilities, able to adapt to unexpected geological conditions, dust storms, or mechanical failures. Future spacecraft would likely function as mobile terraforming hubs, arriving at target planets carrying not only colonists but also entire ecosystems of technology, biology, and artificial intelligence designed to work together. Some futurists imagine self-replicating machines that can build copies of themselves using planetary resources, gradually expanding industrial capacity across the surface of a world. While such concepts raise concerns about control and safety, strict programming constraints could ensure these systems always prioritize environmental stability over unchecked expansion. Another fascinating technology is the concept of orbital climate engineering. Satellites could act as climate regulators, adjusting sunlight exposure across planetary regions, helping manage seasonal variations, and preventing extreme weather events from destabilizing early ecosystems. These satellites would function like planetary weather gods, gently balancing heat distribution across hemispheres. They could also help manage water cycles by directing heat to specific regions to encourage controlled evaporation and rainfall patterns. Such precision climate management would be essential during the fragile early stages of terraforming when ecosystems are still developing and vulnerable. Biotechnology would also advance dramatically. Scientists might engineer plants capable of surviving in lower gravity environments, with stronger root structures and flexible cellular membranes to withstand Martian winds and temperature swings. Genetic engineering could allow photosynthetic organisms to operate efficiently under dimmer sunlight conditions found on planets farther from stars. These modified organisms would not be unnatural intrusions but carefully designed extensions of evolutionary principles, guided by knowledge of genetics and ecology. Some future ecosystems might include hybrid biological-mechanical organisms, where living tissues and synthetic materials merge into resilient planetary life forms capable of surviving harsh climates while contributing to atmospheric regulation. Communication systems would also evolve to support long-duration planetary projects. AI-driven governance systems might help coordinate terraforming efforts across Earth and colonies on other planets, ensuring consistent long-term strategy despite political changes on home worlds. Because terraforming spans centuries, decision-making structures would need to be resilient to social shifts, maintaining commitment to environmental stewardship over short-term economic pressures. Perhaps the most important role of technology will be patience itself. Future machines will not be designed for speed, but for endurance. They will measure progress in centuries, tracking slow atmospheric improvements, monitoring biological spread, and adjusting engineering systems with almost organic subtlety. Terraforming technology will resemble an ecosystem rather than a factory, with AI, biology, and physics working in harmony. In this vision, technology does not dominate nature but collaborates with it, acting as a translator between human intention and planetary physics. As we imagine these future terraforming technologies, we begin to realize that the true breakthrough is not a single invention, but the creation of systems capable of thinking like planets: slow, stable, self-correcting, and patient. These technologies would allow humanity to extend life beyond Earth while maintaining balance and sustainability, ensuring that new worlds do not simply become replicas of old mistakes, but become wiser, more harmonious homes for life to flourish. Living on a world that is still being transformed would feel neither fully alien nor completely familiar, but something beautifully in between, like standing at the edge of a dream where Earth's memory and a new planet's identity slowly merge together. On early terraformed Mars, cities would likely begin as protected habitats, vast dome-like structures built to hold breathable air while the outside environment gradually becomes more hospitable. These domes would glow softly under the thin reddish sky, reflecting sunlight like quiet lanterns across endless plains of dust and stone. Inside these habitats, daily life would feel surprisingly normal. People would wake to artificial sunlights simulating Earth-like daylight cycles, work in hydroponic farms growing food in controlled environments, and gather in community spaces designed to mimic Earth's natural environments, indoor rivers, simulated forests, and slowly expanding ecological zones. Children born in these cities would grow up with a different sense of nature. Instead of visiting forests as distant vacation destinations, they would watch ecosystems slowly grow outside their windows across decades, seeing moss spread across slopes and shallow lakes widen year after year. Transportation across the transforming planet would also evolve slowly. Early settlers might rely on underground rail networks to travel between settlements, avoiding harsh surface conditions like dust storms and radiation exposure. As the atmosphere thickened and weather patterns became more stable, lighter aircraft could begin flying short distances, gliding through thicker air currents above valleys filled with growing vegetation. Eventually, as pressure increased, open-air vehicles might replace sealed transport systems, allowing travelers to feel wind against their faces for the first time on another world. The experience of weather itself would be deeply emotional for inhabitants. Rainstorms would not be violent or sudden but gentle, almost ceremonial, as the planet relearned how to cycle water. People might gather outside to listen to rainfall striking soil that had not felt water for billions of years, treating each storm like a celebration of planetary rebirth. Food culture would change as well. Early settlers would depend heavily on synthetic agriculture and lab-grown proteins, but over centuries, as soil ecosystems matured, more traditional farming could emerge. Crops would need to be genetically adapted to lower gravity and different atmospheric chemistry, producing plants that grow slightly taller, bend more easily under weaker gravitational pull, and use water more efficiently. Cooking traditions might blend Earth heritage with new planetary resources. Families could pass down recipes designed for Martian-grown ingredients, creating new cultural identities rooted in both Earth ancestry and planetary adaptation. Social life on a terraforming world would likely be shaped by patience. People would grow accustomed to living in partially complete environments, understanding that they are not merely residents of a planet but participants in its transformation. Festivals might celebrate planetary milestones. The first year oxygen levels rise slightly, the first stable lake that survives an entire winter season, the first region where humans can safely remove breathing masks outdoors for short periods. Scientific monitoring would become part of daily life, with citizens receiving updates about climate progress as naturally as weather forecasts are received today. Architecture would evolve alongside the environment. Buildings would be designed to adapt as atmospheric pressure increases, with modular structures that can open to the outside environment gradually over centuries. Early structures would be thick and protective, built to shield inhabitants from radiation and cold temperatures, but later generations might design lighter, more open cities with terraces, outdoor gardens, and public spaces that allow natural wind and sunlight to flow freely. Urban planning would prioritize harmony with ecological expansion rather than dominance over it. Psychologically, living on a terraforming world would create a unique sense of time. People would think in generational horizons rather than immediate outcomes. Grandparents might tell stories about what the planet looked like in their youth, describing skies that were once thinner and dustier, lakes that were once smaller, and ecosystems that were just beginning to grow. Such storytelling would become a form of cultural memory, preserving the history of planetary transformation just as human civilizations preserve their historical origins. Entertainment and art would also evolve. Artists might create works that change over time, planting living sculptures made from biological materials that grow, shift, and adapt with climate changes. Music might incorporate natural planetary sounds, wind patterns, rainfall rhythms, and atmospheric pressure fluctuations, blending science and art into a shared cultural experience. Ultimately, daily life on a terraforming world would feel like living inside a story that is still being written. People would not experience planetary transformation as dramatic spectacle but as quiet progress visible only when compared across decades. The planet would slowly shift from engineered environment to natural ecosystem, and future generations might forget that their world was once barren. And that is perhaps the most beautiful outcome of terraforming, when change becomes so complete and so natural that it no longer feels like transformation at all, but simply like home. As centuries pass and Mars slowly transforms beneath a thickening sky, human settlements would evolve from survival outposts into true civilizations with their own culture, politics, and artistic identity, no longer simply extensions of Earth but societies shaped by the unique rhythm of another planet. Early cities would begin as clusters of domed habitats connected by tunnels and climate-controlled corridors, but as the atmosphere becomes denser and radiation levels decrease, these structures would slowly open outward, expanding into layered urban landscapes built along ancient canyon walls and near newly formed rivers. One of the most striking visual features of future Martian civilization would likely be vertical cities, rising along cliff faces where gravity is slightly weaker, allowing architecture to stretch upward in elegant, towering forms that seem to float against the pale sky. These cities would glow softly at night, powered by renewable energy systems that capture wind energy from Martian storms and solar energy from the distant sun, creating light patterns that drift across urban skylines like slow-moving constellations. Martian culture would develop its own artistic language, blending Earth traditions with new planetary experiences. Artists might create works inspired by the color of Martian sunsets, which would likely appear deeper and more blue-tinted as the atmosphere thickens. Music would evolve to match the slower atmospheric pressure rhythms and longer wind patterns, creating compositions that feel spacious and reflective rather than fast and energetic. Literature would focus heavily on themes of time, patience, and planetary transformation, reflecting the long history of terraforming efforts. Children would grow up learning both Earth history and Martian history, studying the story of how life was carefully introduced and nurtured across centuries. Over time, a distinct Martian identity would emerge, shaped by the experience of living on a world that was once engineered but gradually became natural. Political systems on Mars would likely evolve differently from Earth's historical models. Because terraforming requires global coordination over centuries, Martian governance would need long-term planning institutions designed to maintain continuity across generations. Some futurists imagine planetary councils composed of scientists, environmental stewards, and cultural representatives whose primary role would be maintaining ecological balance rather than managing economic competition. Laws might be written with environmental stability as a core principle, ensuring that industrial expansion never disrupts planetary ecosystems. Conflicts between economic growth and environmental protection would likely be resolved through advanced climate modeling systems that predict long-term consequences of development decisions. Martian cities would also prioritize sustainability. Buildings might be constructed from local minerals and bioengineered materials that can repair themselves if damaged. Public transportation could rely on magnetic levitation tracks embedded beneath city surfaces, reducing noise and pollution. Energy grids would be decentralized, allowing communities to remain functional even during planetary storms or technological disruptions. Water management would be especially important, with cities built near natural water basins or underground aquifers to maintain stable supplies. Recycling would be absolute rather than partial, ensuring that every resource is reused in a closed ecological loop similar to planetary natural cycles. Religion and philosophy might also evolve in unique ways. Some Martian cultures might develop spiritual traditions centered around planetary rebirth, viewing terraforming as a sacred collaboration between humanity and the cosmos. Others might focus on scientific spirituality, finding meaning in the slow transformation of climate systems and ecosystems. Rituals could be tied to planetary events, such as seasonal changes in atmospheric pressure or the arrival of long winter dust storms that gently reshape the landscape. Social relationships would also change in response to planetary conditions. Communities might be smaller and more tightly connected, since long-distance travel could still be difficult during early civilization stages. Family structures might expand to include multi-generational households, emphasizing continuity of knowledge across long periods of planetary development. Education would likely be lifelong, because scientific understanding of the planet would constantly evolve as terraforming progresses. Ultimately, future Martian civilization would represent a fusion of technology, ecology, and culture. It would not be a copy of Earth's societies but a new civilization shaped by slower time rhythms, stronger environmental awareness, and a collective understanding that they live inside a planetary experiment spanning centuries. Martian civilization would stand as a testament to humanity's ability not only to survive in space, but to build meaningful culture within it. And as cities grow beneath increasingly blue skies, future Martians might look upward at Earth as a distant ancestral home, just as humanity once looked upward at Mars and dreamed of what might be possible. For all its beauty and promise, terraforming also carries shadows, because when entire planets are being transformed, even small mistakes can grow into planetary-scale consequences. The dream of reshaping worlds is powerful, but nature does not always respond predictably to intervention, and climate systems are complex webs of feedback loops that can shift suddenly if pushed too far. One of the greatest dangers would be runaway climate effects. If too many greenhouse gases were released too quickly while attempting to warm Mars, temperatures could rise beyond safe levels, melting subsurface ice too rapidly and releasing additional trapped gases in a self-amplifying cycle. Though Mars is far from the Sun compared to Earth, such instability could still create localized climate extremes, potentially destroying early ecosystems that were still fragile and developing. Terraforming requires careful balance. Because planetary systems rarely respond linearly, small inputs can sometimes produce disproportionately large outcomes. Another risk would be atmospheric loss. Even after years of engineering effort to thicken the Martian atmosphere, solar wind and radiation could slowly strip molecules away if protective magnetic shielding systems failed or were not strong enough. The atmosphere might appear stable for decades, only to gradually thin again over centuries if maintenance systems were neglected. This introduces a new type of dependency. Civilizations would need to continuously maintain planetary climate infrastructure much like cities maintain infrastructure today, but on a much larger and longer time scale. If political or economic systems on Earth or Mars were to collapse, terraforming progress could stagnate or reverse. Biological risks would also be significant. Introducing Earth organisms to another world carries the possibility of ecological imbalance. Some engineered species might grow too aggressively, outcompeting other organisms and creating monocultures instead of balanced ecosystems. Without natural predators and complex evolutionary pressures, early Martian ecosystems could become unstable. Scientists would need to carefully monitor biodiversity, introducing species gradually rather than releasing large populations at once. There is also the possibility of genetic mutation under different radiation and gravity conditions, leading to unexpected evolutionary outcomes that might disrupt ecological stability. Technological risks must also be considered. Self-replicating machines, while powerful tools for terraforming, could theoretically malfunction or behave unpredictably if programming safeguards fail. In extreme speculative scenarios, autonomous systems might overconsume planetary resources in attempts to fulfill poorly defined objectives. Future terraforming AI would need strict ethical and environmental constraints, ensuring that machine intelligence prioritizes planetary health over industrial efficiency. Human risks would also be psychological and social. Living on a world that is still being shaped could create generational fatigue. Some people might feel disconnected from Earth's history, while others might resist planetary transformation entirely, preferring to preserve Mars in its natural state. Political conflict could arise between groups advocating for rapid terraforming progress and those favoring conservation or slower development. Managing these social tensions would be just as important as managing climate systems. Natural disasters would remain a threat even on a partially terraformed planet. Dust storms, though potentially less violent in thicker atmosphere conditions, could still occur and affect solar energy infrastructure and transportation. Geological instability might also pose risks if volcanic or tectonic activity is present beneath the surface. Early settlements would need robust disaster response systems capable of functioning independently during environmental emergencies. Perhaps the most subtle danger would be overconfidence. Humanity might believe that planetary engineering makes nature fully controllable, but planets are dynamic systems influenced by countless variables that cannot always be predicted. Terraforming success would require humility, constant observation, and willingness to adjust or even reverse interventions if necessary. Despite these risks, the possibility of failure does not necessarily make terraforming unwise. Rather, it makes it more important to approach carefully. Every great expansion of life across history has involved risk. Earth's own biosphere was transformed by early microbial life, sometimes causing mass extinctions but also enabling new evolutionary opportunities. Terraforming would represent a continuation of that long history of planetary experimentation, but conducted with greater knowledge and responsibility. In the end, the greatest disaster would not be technical failure, but ignoring caution altogether. Terraforming must remain a careful balance between ambition and respect for planetary systems, because a world once damaged may take far longer to heal than it took to change. And so the dream continues forward, but slowly, carefully, with eyes always open to both possibility and danger. As humanity looks beyond its home world and begins to shape other planets, a deeper question emerges that goes far beyond engineering or survival. What does it truly mean for life to expand into the cosmos? Cosmic expansion is not only a physical process of traveling to new worlds, it is also a philosophical journey about identity, purpose, and humanity's place in an enormous, silent universe. For most of human history, Earth was perceived as the center of experience, the only stage upon which consciousness could thrive, but modern astronomy has revealed something far more humbling and awe-inspiring. The universe is vast beyond comprehension, filled with billions of galaxies, each containing billions of stars, many of which may host planets similar to Earth. In such a universe, life may either be extraordinarily rare or astonishingly widespread, and terraforming becomes part of a larger question about whether life should actively spread itself across cosmic distances or remain quietly confined to its origin. Some philosophers argue that life has an inherent tendency to expand. On Earth, life has continuously spread across oceans, continents, and atmospheric layers whenever conditions allowed. From this perspective, terraforming and space colonization are not acts of domination but natural extensions of biological evolution. Conscious intelligence may simply be the universe becoming aware of itself and seeking to diversify its own forms of existence. Spreading life to other planets could increase the universe's biological and cognitive diversity, ensuring that knowledge, culture, and consciousness continue even if Earth faces catastrophic events such as asteroid impacts, solar changes, or human-made environmental damage. Other thinkers caution against aggressive expansion. They argue that not every planet needs to be transformed into a habitat for human life. Some worlds might be valuable precisely because they remain untouched, serving as natural laboratories for studying cosmic processes. This perspective emphasizes humility, suggesting that humanity should act as a caretaker rather than a conqueror of space. Instead of transforming every world, perhaps humans should selectively terraform only planets where life cannot otherwise develop, leaving potentially habitable but empty worlds to evolve naturally. Cosmic expansion also influences human psychology. Living in a universe where new worlds can be created for life may reduce existential fear. Humanity would no longer be limited to a single planetary home, which could change cultural attitudes toward risk, exploration, and long-term planning. People might think of themselves as citizens not just of Earth or Mars, but of a broader interplanetary civilization connected by shared responsibility for maintaining life across worlds. Religion, art, and mythology would likely evolve alongside cosmic expansion. New belief systems might emerge centered around the idea that life itself is sacred cosmic energy, constantly moving and adapting. Artistic expressions might reflect cosmic landscapes, star patterns, and planetary ecosystems. Literature might focus on long-term planetary stories rather than individual hero narratives, emphasizing collective progress over personal achievement. Perhaps the most profound philosophical implication of terraforming is the realization that humanity is becoming a species capable of shaping not just its own environment, but planetary environments themselves. This creates a new moral responsibility. Power at such a scale requires wisdom, patience, and ethical reflection. Cosmic expansion should not be driven purely by curiosity or technological pride, but by a desire to preserve and spread life in ways that respect both cosmic beauty and planetary balance. Ultimately, the philosophy of cosmic expansion suggests that terraforming is not just about building new homes for humanity, but about participating in the larger story of life in the universe. If life is rare, then spreading it becomes an act of cosmic preservation. If life is common, then terraforming becomes a way of joining a larger community of living worlds. Either way, the expansion of life into space represents a new chapter in evolution. Not just biological evolution, but cultural, ethical, and philosophical evolution as well. And as humanity looks toward distant stars, it carries with it not only technology and science, but also questions about meaning, purpose, and its place in the silent cosmic ocean. One of the most profound possibilities in the future of space exploration is the discovery of life that did not originate on Earth, because finding alien life would change everything about how humanity approaches terraforming, exploration, and ethics in space. The universe is vast, and many scientists believe that life may exist beyond Earth in microbial or primitive forms, hidden beneath icy surfaces, inside subsurface oceans, or within chemical environments very different from those found on our home planet. If such life were discovered, it would no longer be possible to view other planets simply as blank canvases for human settlement. Instead, they would become living ecosystems deserving protection and study. Mars would be one of the first places where scientists would carefully search for alien microbial life. Subsurface ice layers, ancient sediment deposits, and underground aquifers could potentially preserve organisms that evolved independently from Earth's biosphere. Discovering even simple microbial life would represent one of the greatest scientific breakthroughs in human history, proving that life may arise multiple times across the universe. Such a discovery would also raise difficult ethical questions. Would humanity have the right to terraform a planet that already contains native life, even if that life is microscopic and difficult to observe? Many scientists would likely argue for strict planetary protection protocols, treating such worlds as biological heritage sites rather than targets for colonization. Beyond Mars, icy moons such as those orbiting gas giants could be even more promising locations for alien life. Subsurface oceans warmed by gravitational tidal forces could create stable environments where microorganisms thrive without needing sunlight. In such environments, life might rely on chemical energy rather than photosynthesis, similar to deep ocean ecosystems on Earth where organisms survive near hydrothermal vents. If alien life were found in such environments, terraforming would likely shift from transformation to preservation. Humanity might instead build habitats in orbit or above the surface rather than attempting to change the planet itself. The discovery of intelligent alien life would create even more complex ethical challenges. If intelligent civilizations were discovered, terraforming would no longer be about spreading life, but about peaceful coexistence. Humanity would need to develop new interstellar diplomatic philosophies, perhaps learning to communicate across entirely different biological and cultural systems. The idea of altering another world inhabited by intelligent beings would likely be considered unacceptable by most ethical frameworks. Even the absence of alien life would be meaningful. If scientists explored many worlds and found no life at all, it would suggest that life might be extraordinarily rare and precious. In that case, terraforming could be seen as an act of cosmic responsibility, spreading life where it does not naturally exist. Some thinkers believe that life has an inherent value that should be expanded and preserved, while others believe that the universe's natural diversity should remain untouched. Future detection technologies would play a crucial role in answering these questions. Advanced telescopes, planetary probes, and atmospheric analysis tools would scan planets for chemical signatures associated with life, such as oxygen imbalance, methane presence, or unusual molecular patterns. These scientific searches would likely occur long before any terraforming attempts began, ensuring that humanity does not accidentally destroy unknown ecosystems. Alien life discovery would also influence human culture. Literature, philosophy, and religion would likely undergo major transformations as humanity reevaluates its place in the universe. The idea that life is unique to Earth would be replaced by a broader cosmic perspective. Art and storytelling would reflect this new understanding, exploring relationships between different forms of life across space. Ultimately, the possibility of alien life makes terraforming both more exciting and more complicated. It forces humanity to move carefully, balancing exploration with preservation. Terraforming would no longer be a simple expansion project but part of a larger cosmic ecological conversation. And as humanity searches the stars, it may discover that the greatest discovery is not transforming other worlds, but learning whether it is alone or part of a much larger community of life scattered across the universe. In the distant future, perhaps centuries or even millennia from now, humanity may stand beneath skies that were once thin and hostile but have become deep, soft, and alive with weather patterns, watching oceans move across continents that were once dry and silent. A fully terraformed world would not feel artificial. Instead, it would feel naturally evolved, as if the planet had simply awakened from a long geological sleep. Mars, if fully terraformed, might eventually possess a thick, breathable atmosphere, stable water cycles, and ecosystems complex enough to sustain independent biological evolution. The sky might appear bluish during daylight, scattering sunlight through denser air much like Earth's atmosphere does, while sunsets could glow with richer colors as dust and atmospheric particles bend light in slow, beautiful gradients across the horizon. Oceans on a fully terraformed world would likely be smaller and shallower than Earth's oceans because of Mars' lower gravity and limited water reserves. However, these oceans would still play a critical role in climate regulation, absorbing heat during daylight and releasing it slowly at night. Coastal regions might become the most populated areas, where cities could stretch along winding shorelines of newly formed seas. Rivers would carve dynamic pathways across continents, constantly reshaping landscapes through erosion and sediment deposition. Over thousands of years, geological processes would begin interacting with biological processes, creating environments that feel less engineered and more naturally balanced. Ecosystems on a fully terraformed planet would likely be carefully balanced mixtures of Earth-origin species and new evolutionary variants adapted to lower gravity and different climate rhythms. Trees might grow slightly taller and thinner, stretching upward towards sunlight in thinner gravitational conditions. Animals introduced to such worlds would need adaptations for survival, including stronger respiratory systems or modified skeletal structures to function efficiently in lower gravity environments. Over time, natural selection would create entirely new species that are descendants of Earth life but uniquely suited to the new planet's environment. Cities on a fully terraformed world would likely be very different from early settlements. Instead of protective domes, architecture could become open and integrated with natural environments. Urban planning might prioritize harmony with ecosystems rather than separation from them. Future cities could include vertical forests, floating transportation networks, and energy systems embedded directly into the environment. Renewable energy would dominate, with solar, wind, and possibly even atmospheric energy harvesting systems providing power. Psychologically, living on a fully terraformed world would change how humanity perceives nature. People might no longer view nature as something separate from civilization, but as something deeply interconnected with it. Environmental stewardship would become a cultural value, passed down through education and social traditions. Children might learn planetary science as naturally as they learn language, because understanding climate and ecosystems would be essential knowledge for daily life. The political structure of a fully terraformed world might also change. Instead of short-term political cycles, governance could focus on long-term planetary stability. Decision-making systems might incorporate artificial intelligence to simulate future climate and ecological outcomes before policies are implemented. Economic systems might shift towards sustainability-focused models that measure prosperity not only in financial wealth but also in ecological health. The most beautiful aspect of a fully terraformed world would be its sense of naturalness. Future inhabitants might forget that their world was once engineered, just as modern humans rarely think about how Earth's current ecosystems evolved over billions of years. Terraforming would become part of planetary history rather than a visible process. The planet would feel alive, self-sustaining, and independent from constant human intervention. Ultimately, a fully terraformed world would represent humanity's greatest achievement, not technological domination, but partnership with planetary systems. It would be a world where life, climate, and civilization move together in harmony. And perhaps, in that distant future, looking at the sky would feel the same as it does on Earth today. Natural, comforting, and filled with endless possibilities. In the farthest visions of the future, humanity may no longer think of itself as a species bound to individual planets, but as a civilization spread gently across star systems, like seeds carried on cosmic winds of technology, knowledge, and time. Interstellar civilization would likely begin not with massive fleets of colonists, but with slow, patient exploration probes sent to nearby star systems, carrying genetic archives, artificial intelligence, and the blueprint of Earth's ecosystems. Traveling between stars is not a journey measured in months or years, but in decades, centuries, or even longer, depending on propulsion technology. Future spacecraft may use advanced fusion drives, solar sails pushed by laser arrays, or even more speculative physics-based propulsion methods that allow near-relativistic travel speeds. As humanity spreads among the stars, civilization would become less centralized. Instead of a single planetary government, humanity might form a network of interstellar societies connected through communication relays and shared cultural values. Information would travel faster than physical travel, meaning that cultural and scientific progress could spread quickly even if people themselves traveled slowly. Artificial intelligence would likely play a crucial role in managing interstellar logistics, planetary engineering, and long-distance communication. Interstellar colonization would also require biological adaptation. Humans living on different worlds might gradually evolve physiological differences due to environmental pressures such as gravity, radiation exposure, and atmospheric composition. Over thousands of years, human descendants might develop subtle physical variations depending on which planets they inhabit. However, cultural unity might remain stronger than biological differences because shared history, language, and knowledge could maintain a sense of collective identity across space. Space habitats would also become important. Instead of terraforming every world, humanity might construct massive artificial living environments such as rotating space stations that simulate gravity through rotation. These habitats could house millions or even billions of people, floating in orbit around stars or planets. Some futurists imagine gigantic structures called megastructures that could capture most of a star's energy output to power advanced civilizations. The purpose of humanity's expansion among the stars might not be conquest but preservation. Spreading life across multiple star systems would protect civilization from cosmic threats such as asteroid impacts, supernova radiation bursts, or long-term stellar evolution. Earth would remain culturally important as humanity's origin world, perhaps preserved as a natural heritage planet, similar to how ancient cities are preserved as historical sites. As humanity becomes a multi-planet and multi-star species, its definition of home would change. Home would no longer be a single place, but a network of worlds connected by shared purpose. People might travel between planets for work, education, or cultural experiences, much like people travel between countries today. Families could span multiple planets, with relatives living under different suns. The greatest challenge of interstellar civilization would not be technology but unity. Maintaining cooperation across vast distances would require strong ethical and cultural frameworks. Humanity would need to balance expansion with preservation, ensuring that new worlds remain sustainable ecosystems rather than repeating environmental mistakes made on Earth. In this distant future, humanity may no longer see itself as separate from the cosmos but as an extension of it. Life would spread like light across darkness, slowly filling empty regions of space with intelligence, culture, and biological diversity. Whether humanity ultimately becomes a dominant cosmic civilization or simply one of many intelligent species among the stars remains unknown. But the journey itself would represent one of the most ambitious stories ever told. The story of life learning to move beyond its birthplace and explore the infinite ocean of space. As the long journey of planetary transformation and cosmic exploration slowly reaches its quiet ending, there is a feeling of gentle peace drifting through the imagination, like falling asleep beneath a sky that has seen billions of years of history unfold. The story of terraforming is not truly about machines or planets, but about life's endless patience and its desire to survive, adapt, and grow. Imagine standing on a distant world in the future, where skies are no longer hostile, where water flows softly across green valleys, and where wind carries the faint scent of new forests growing slowly beneath a second sun. The transformation of planets would feel less like construction and more like memory returning, as if the universe itself were learning how to breathe through life spreading across its empty spaces. Stars would continue to burn silently above, ancient and indifferent, yet humanity would now exist not as a visitor to the cosmos but as a participant in its unfolding story. In this final reflection, the journey returns to Earth, the birthplace of everything humanity has ever known. From space, Earth would still glow with deep oceans and swirling clouds, still holding the history of civilization within its atmosphere. Perhaps future travelers would look back toward Earth not with sadness, but with gratitude, understanding that their expansion into space was only possible because life first learned how to thrive on a single fragile planet. Terraforming other worlds would not replace Earth but extend its legacy, like branches growing from a single cosmic tree. Children of future star civilizations might learn stories about how humanity once struggled to survive under one sky before learning to carry life outward into darkness. The final vision of terraforming is not loud or dramatic. There are no explosions of creation, no sudden planetary transformations. Instead, there is quiet beauty, slow rain falling on distant continents, oceans breathing with tides, ecosystems growing steadily without interruption. Time itself becomes part of the artwork, shaping worlds through centuries of careful balance. Future civilizations might celebrate planetary anniversaries, remembering the first drops of rain, the first stable oxygen levels, the first time humans could walk outside without protective suits. And then, like a cosmic lullaby, the story reminds us that the universe is vast, but life makes it feel smaller and warmer. If humanity succeeds in spreading life among the stars, it will not be through domination or conquest, but through patience, science, cooperation, and respect for nature's slow rhythms. The final message of terraforming is not that humanity will change the universe, but that humanity will learn to grow with it. As the documentary fades into darkness, stars remain, countless and quiet, waiting for life to continue its journey. And somewhere, on some distant world, wind may already be moving across new oceans, carrying the first whispers of life across alien lands. And now, as the journey reaches its final breath, the universe seems to slow its heartbeat, like a giant sleeping peacefully after telling a very long story across stars, planets, oceans, and centuries of imagination. The dream of terraforming gently fades into something deeper, not an ending, but a soft resting point where humanity, technology, and nature all learn to coexist without struggle. Imagine drifting through space with no sound except the quiet vibration of distant starlight, watching countless terraformed worlds rotate slowly beneath new skies, each one carrying its own history of life's persistence. The story of terraforming was never really about building new planets. It was about proving that life is not fragile in spirit, even if it is physically delicate. Life continues because it remembers how to adapt, how to survive cold nights, how to grow roots in unfamiliar soil, and how to turn darkness into possibility. In this final vision, humanity is no longer rushing forward with ambition, but moving slowly, peacefully, like a civilization that has learned wisdom from time itself. Interstellar ships drift quietly between star systems, not as symbols of conquest, but as seeds of biodiversity carried across cosmic winds. Future generations may look back at the first pioneers of terraforming with deep respect, knowing that they began something they could never personally finish. Their work became a promise to the future rather than a victory for the present. Children of distant worlds may grow up never seeing Earth, yet still feel connected to it through stories, history, and shared biological ancestry. The cosmos itself feels softer in this ending, not empty, but patient. Stars continue to burn, galaxies continue to spin, but now life exists as a companion to cosmic time rather than a brief accident inside it. Terraforming has taught humanity something profound, that power is not measured by how quickly we can change a world, but by how gently we can help it change itself. The greatest technology of the future may not be machines or AI systems, but wisdom, the ability to know when to act and when to wait, when to build and when to listen to the natural rhythms of planets and ecosystems. And so, as the final image fades, there is only quiet space, filled with soft glowing stars, slow-moving planets, and distant worlds where rain may someday fall on soil that once knew only dust. Somewhere, on one of those worlds, life is growing quietly, learning how to breathe new air beneath new skies. The story of terraforming does not end with humanity conquering space. It ends with humanity becoming part of space, not as rulers, but as caretakers of life's long journey across the universe.